Hello and welcome back. In this section, we're going to talk about Docker container networking. We'll cover different types of networks used in Docker world and how to create your own user-defined networks. In the first lecture, we'll give a brief introduction to Docker container networking. Let's start by taking a look at Docker's default network model. Docker uses the networking capabilities of the host machine operating system to provide networking support for the containers running on the host machine. Once the Docker daemon is installed on the host machine, a bridge network interface, Docker 0, is provisioned on the host, which will be used to bridge the traffic from the outside network to the internal containers hosted on the host machine. Each container connects to the bridge network through its container network interface. Containers can connect to each other and connect to the outside world through this bridge network interface. This is how the default Docker network model called bridge network looks like. There are actually 4 different types of Docker networks: closed network, which is also called non-network, bridge network, host network, and overlaid network. We'll deep dive into each of those 4 different networks in the following lectures, so that you can make an educated decision to choose which Docker network model to use when creating Docker containers. Before we finish this lecture, I want to show you how to check the existing Docker networks on your laptop. Just bring up a terminal and type docker network ls. By default, these should be 3 networks created out of the box when Docker is installed on your laptop: the bridge network, the host network, and the non-network. That's it for this lecture. I hope you've enjoyed it. Hello, and welcome back. In this lecture, we're going to talk about the non-network. This network does not have any access to the outside world. The non-network adds a container to a container-specific network stack. That container lacks a container interface, so it's totally isolated. This kind of container is called closed container. Let's see it in action. In order to create a closed container, we can use the --netnone option in the docker run command. Here, we do docker run --netnone busybox sleep 1000. This should start up a closed container in the non-network from the busybox image. Sleep 1000 should keep the container in running state. Now, let's log into the container and verify that this is indeed an isolated container. We copy the container ID first. Do docker exec-it. Paste the container ID and do /bin/ash. In case you don't know ash, ash is a very lightweight Unix shell. Busybox is a tiny Linux distribution which comes with ash instead of bash shell. Now we're logged inside the container. To verify we're disconnected from the outside world, we can ping Google public DNS, which is 8.8.8.8. If we ping this IP from our host machine, as you see, there is no problem to reach Google public DNS. If we ping this IP from the closed container, the IP is unreachable. This container is isolated from the outside world. Now we run ifconfig command inside the container to list all the network interfaces of the container. As you see, there is only one network interface. This is a special type of interface called loopback interface. It is not connected to any networks and is assigned a special IP address 127.0.0.1. It is mainly used by internal applications on the local host machine to communicate with each other. The biggest benefit of this isolated network model is that it provides the maximum level of network protection because the containers cannot be reached from outside the host. However, this network model won't be a good choice if network or internet connection is required. For example, if the application requires making HTTP requests to the outside world. This isolated network suits well where the container requires the maximum level of network security and network access is not necessary. That's it for this lecture. I hope you have enjoyed it. Hello, and welcome back. In this lecture, we're going to talk about another network model, the bridge network model. This is the default type of networks in Docker containers. All the containers in the same bridge network are connected with each other, and they can connect to the outside world via the bridge network interface. Let's see it in action. Here, I'm at a new terminal. We do docker network ls to list all the Docker networks on my localhost. Docker creates a default bridge network called bridge when Docker daemon is initialized. We can check out the details of this bridge network by running docker network inspect command. As you see, the subnet 172.17.0.0/16 is allocated for this bridge network. The IP range of this subnet is from 172.17.0.0 to 172.17.255.255. Now let's fire up our first container on this bridge network. Just do docker run -d --name. We name the container container_1. This time, we run the busybox image as well. Then sleep for 1000 seconds. In this docker run command, we don't specify --net flag. The built-in bridge network will be automatically chosen for the container. Now the container is up running. Let's run ifconfig inside the container to list all the network interfaces of the container. As you see, there are two network interfaces, a loopback interface and a private network interface. The loopback interface is the same as the one of the closed container of the previous lecture, which is 127.0.0.1, and is used for internal applications and can be connected to the outside world. The private network interface is connected to the bridge network. As we have demoed previously, the bridge network on the host machine has the IP range between 172.17.0.0 to 172.17.255.255. This network interface is exactly within the range. It can be used to access other containers in the same bridge network. Let's prove that. Here, we fire up another container, container_2, in the same bridge network. If we list all the network interfaces of this container, as you see, the private network interface of the second container is 172.17.0.3, which is also within the IP range of the bridge network. Now, let's ping container 2 from container 1. As you see, container 1 can reach container 2 by IP via the private network interfaces of each other. Containers can also use this private network interface to connect to the outside world. Let's ping 8.8.8.8 from container 1. See? We can reach the Google's public DNS from this container. Now, we can demo containers within the same bridge network can connect to each other. They can also connect to the outside world. However, by default, different bridge networks are isolated from each other. Containers within one bridge network can access to containers within another bridge network. Let's demo that. Here, we create another custom bridge network. The command to create a Docker network is docker network create. Docker network create command takes a -- driver option, which specifies the driver of the network. We use the bridge driver to create a bridge network. Then, we need to give the new network a name. Just name it my bridge network. Now, the network has been created. If we do docker network ls, we can find out the newly created Docker network. Let's check out the IP range of this new network. The subnet is 172.18.0.0/16, and the IP range is from 172.18.0.0 to 172.18.255.255. Let's fire up container 3 from the new bridge network. Just add a -- net option and add the name of the new bridge network. Now, if we check the IP of container 3, we can see it is within the IP range of the new bridge network. Next, we get the IP of container 1 and ping container 1 from container 3. As you see, we can't reach container 1 from container 3 because they're within different bridge networks, and each bridge network is isolated from each other. But Docker has a feature which allows us to connect a container to another network. Once connected, the container can communicate with other containers in the same network. This is done via the Docker network connect command. Let's see how it works. Here, we want to connect container 3 to our old bridge network. So we can do Docker network connect bridge container 3. Now, if we list the network interfaces of container 3 again, we can see container 3 has one extra network interface, which is exactly within the range of our old bridge network. Now, if we ping container 1 from container 3 again, see, we can reach container 1 this time, as container 3 has already connected to our old bridge network. We can also disconnect container 3 from the old bridge network. Just do Docker network disconnect bridge container 3. Now, if we list the network interfaces, we can see the just added network interfaces has been removed. Let's recap. In this lecture, we have demoed the bridge network model. In a bridge network, containers have access to two network interfaces. The loopback interface, which does not have network access to the outside, and a private interface, which is connected to the bridge network of the host. This is the one used to connect to the outside network. All containers in the same bridge network can communicate with each other. Containers from different bridge networks can't connect with each other by default. But we can manually connect a container to another bridge network. Bridge network is the most common network model in Docker. Comparing with the non-network we introduced previously, bridge network reduces the level of network isolation in favor of better outside connectivity. A bridge network is most suitable where you want to set up a relatively small network on a single host. That's it for this lecture. I hope you've enjoyed it. In this lecture, we're going to talk about host network model and overlay network model. Let's start by introducing the host network. The host network is the least protected network model. It adds a container on the host's network stack. Containers deployed on the host stack have full access to the host interface. This kind of containers are usually called open containers. To create open containers, we just add --net host flag to the Docker run command. Next, let's list all the network interfaces of this container. As you see, this container has all the network interfaces on the host machine. All of the network interfaces defined on the host will be accessible to the container. Host network is the type of network models with a minimum network security level. There is no isolation on this type of open containers. Thus, leave the containers widely unprotected. However, the host network does bring one benefit, which is performance. Containers running in the host network stack should see a higher level of performance than those traversing the Docker 0 bridge and IP tables port mappings. I personally haven't used host network in production. You should use this network model only when you have a valid reason. The last network model we would talk about is the overlay network. All the network models we have covered previously, including none, Bridget, and host network, all have one limitation, which is they can only be deployed on single host. If you want to create a network across multiple host machines, you would need the overlay network model. Docker Engine supports multi-host networking out of the box through the overlay network driver. Unlike bridge networks, overlay networks require some pre-existing conditions before you can create one. One option is that when Docker Engine is running in Swarm node, you can create an overlay network on a manager node. Or if you are not using Docker Engine in Swarm mode, the overlay network would require a key value store service. In real-life scenarios, most services are deployed across multiple hosts, so overlay network is widely used in production. Docker is making a network configuration easier and more transparent to us. The latest Docker Swarm mode will create the overlay network automatically for you. Usually, we do not need to customize configuration, so we won't cover much about overlay network in this course. If you're interested in learning more about it, take a look at the next lecture. In the previous lectures, we have seen how to create Docker networks through Docker network create command. But in most cases, our Docker workflow is automated by Docker Compose. In this lecture, we'll learn how to define network models through Docker Compose file. By default, Docker Compose sets up a single network for your services. Each container will join the default network and is reachable by other containers on that network. Let's see how it works. Here we do git stash and git checkout v 0.4. Then we run Docker Compose up to fire up the Redis and Docker app containers. As you see, Docker creates network Docker app _ default with the default driver. The prefix of the default network name, which is Docker app, comes from the name of the current directory. The default driver of this network is the bridge driver. We can verify it by running docker network ls command. When we stop all the containers by running docker compose down command, the created network will be removed as well. Instead of just using the default network, you can specify your own networks with the top-level networks key in the Docker Compose file. Let's see it in action. Just open up the Docker Compose file. Let's add a network key at the same level as the services key. Then we can name our network my_net in the driver option. We just specify the bridge driver. After we have defined our custom network, myNetwork, we can specify what networks each service can connect to with the service level networks key, which is a list of names referencing entries under the top-level networks key. In our case, we will add myNet for both Redis and Docker app services. Now we can save the Docker Compose file. Then fire up all the containers again by running Docker Compose up. As you see, this time it creates the Docker app _ my_net as the network. We can even create more complex network topologies. Take a look at the following Docker Compose file. It defines two custom networks, the front network and the back network. It defines three services: proxy, app, and DB services. The DB service is deployed on the back network. The proxy service is isolated from the DB service because they do not share a network in common. Only app can talk to both. This provides some sort of network isolation between services. These network isolation tricks are very popular on multi-tier applications. That's it for this lecture. I hope you've enjoyed it. In this lecture, we'll see how we can write some unit tests for our application and run those tests inside a container. These unit tests should test some basic functionality of our Docker app code with no reliance on external services. Ideally, all tests, in particular unit tests, should run as quickly as possible so that developers can iterate much faster without being blocked by waiting for the test's results. Docker containers can be spun up in seconds and can create a clean and isolated environment, which is a great tool to run unit tests with. We'll be using a Python unit testing framework called Unit Test to write unit tests. Here are some examples of the unit tests. Since writing unit tests is not the main focus of this course, I have already written down the test cases and uploaded to GitHub. You can download the source code by running git stash and git checkout v0.5. Let me quickly walk you through the unit test file. Just open the current directory and then open the test.py file. This is a very simple test file with 2 test cases and a setup method. This setup method will run before each test case and it initializes a test version of our Docker app. The first test case calls the /URL with a key value pair and sets the submit value to save. This basically tests the behavior when we click the save button on the front end and verifies that the application returns a 200 status code and displays the key value pair we submitted. The second test case calls the /URL as well with a key value pair and sets the submit value to save, which is exactly the same as the first test case. Then it calls the URL/ again with the same key and set the submit value to load. This is a quite simple test file, but how can we run this test suite in a container? We first build all the containers. There is a new Docker compose command for us to learn. Docker compose run. Docker compose run will run a one-time command against a service inside a container. Here we can do Docker compose run, then type the service name, which is Docker app. The command we want to run here is python test.py, which will run our test suite. The default command defined in the Docker file for the Docker app service is python app.py, which runs our app. But now we are overriding the default command so that we can run our test file instead. Just hit enter. See? All the tests passed. In our case, we have incorporated the test for our application into our Docker app image. In this way, a single image is used through development, testing, and production. This allows us to easily check the tests in images running at different environments, which greatly ensures the reliability of our tests. The downside of this approach is that it increases the size of the image. In general, if your test files are not that large, it is recommended to include the tests in the image for the sake of simplicity and reliability. That's it for this lecture. I hope you've enjoyed it. Hello and welcome back. In the next few lectures, we'll be looking into how we can fit Docker into our continuous integration process. In case you don't know what is continuous integration is a software engineering practice in which isolated changes are immediately tested and reported when they're added to a larger code base. The goal of continuous integration is to provide rapid feedback so that if a defect is introduced to the code base, it can be identified and corrected as soon as possible. Let's take a look at how a typical continuous integration process without Docker involved looks like. So we have got developers checking out code into our local repository. When they get some features done, they commit the changes to the central repository. The continuous integration server keeps monitoring the central repository. Upon a commit, this would usually trigger a build on the continuous integration server. The build process might vary from application to application, but normally it would involve checking out the latest code base, building the application, and running unit and integration tests. The continuous integration server would also assign a build label to the version of the code it just built. The continuous integration server can also be configured to deploy the application to staging or production server after it validates the build. Next, let's take a look at how Docker can fit into this continuous integration process. In a world with Docker, what usually happens is that the continuous integration server would build the Docker image after it has built the application. The application goes inside the image, and continuous integration server pushes the image to a Docker registry. Then on the other side, you can pull the newly built image from Docker registry and run the application inside the container on another host. It can be development, staging, or even production environment. In this and next few lectures, we'll be setting up a continuous integration workflow using GitHub as the central repository and CircleCI as the continuous integration server. GitHub allows you to host public Git repositories for free, while CircleCI is a hosted continuous integration solution which allows you to run one concurrent build for free. So you can register your own GitHub and CircleCI account to follow along this course. And we'll hook up the GitHub account and the CircleCI account so that upon any new changes made into the GitHub repository, it'll automatically trigger a build on the CircleCI server. During the build, we'll build the image and run the unit tests inside the container. Let's start by registering yourself a GitHub account. If you already have one, feel free to skip this step. Now, I'm at the GitHub signup page. Just provide a user ID, your email address, and password continue. Here, we choose the free plan, which will allow us to host public repositories. Now, the repository is complete, and we're logged in as the new user ID. Next, I'll show you how to fork my Docker app repository, which will create a copy of the repository under your user ID and allow you to freely experiment with changes without affecting the original repository. Now, just go to my GitHub repository, https://github.com/jlee tutorial Docker app. Now we have opened the Docker app repository. Let's click the Fork button to fork the repository. See? We have got our own version of Docker app repository. In the rest of this lecture, I'll demonstrate how to set up the SSH key for your GitHub account so that we can push changes from your local box to the central GitHub repository more easily. SSH keys are a way to identify trusted computers without involving passwords. You can generate a SSH key pair and save the private SSH key in your local box and add the public key to your GitHub account. Then you can directly push your changes to GitHub repository without typing password. First, you should check if you already have the SSH key available in your local box. The public key file usually sits under the hidden SSH directory in your home directory, and it usually ends up with .pub extension. I don't have an SSH key pair in this computer, so I will go ahead and create one. If you already have one, feel free to skip this step. Now, let's follow the instruction on the GitHub website to create a SSH key pair. Just copy the SSH keygen command to your terminal to create a SSH key. Here, we stick with the example email address. Just keep hitting enter to go with the default options. The private key and public key have been generated. What we'll do next is to start SSH agent in the background and add the SSH key to the agent. Now, let's copy our SSH public key to the clipboard so that we can add it to the GitHub. Finally, we go back to the GitHub profile and click the settings. SSH key and CPG keys. Click New SSH key and give the public key a title. And paste the public key here and click Add. There you go. The public key has been added to the GitHub. That's it for this lecture. In the next lecture, we'll configure a Circle CI account and hook it up with a GitHub account to set up the continuous integration workflow. Hello, and welcome back. In this lecture, we'll learn how to link Circle CI with our GitHub repository to set up a continuous integration workflow. The Circle CI build steps are defined in a config.yaml file in a directory called .circleci, which should be checked in to the root directory of the Git repository. I have already uploaded the configuration YAML file to the GitHub repository. Let's check out the repository and take a look at what the configuration file looks like. You can go to the forked Docker app repository under your GitHub account. Make sure you go to the forked repository under your GitHub ID, not the original one. Otherwise, you wouldn't have permissions to push changes to the repository. And click the Clone or Download button, which displays the Git clone URL for you to download the repository. Here, you need to select using SSH instead of using HTTPS. Next, just click the clipboard icon to copy the URL to your clipboard. Then we go back to the terminal and do git clone and paste the URL. Then put -b v0.6 so the Git will download repository locally, and checkout tag v0.6. After the download is complete, let's enter the Docker app repository and open it with Sublime text. As you see, we have added a config.yaml file in a directory called .circleci. Let's open the YAML file. Next, let me quickly walk you through what the configuration YAML file does. We always start with the version. This version 2 defines that we're using the version 2 format of CircleCI, which uses the most recent feature of CircleCI at the time when I recorded this lecture. Next, we have a jobs key. Every config file must have a build job. This is the only job that will be automatically picked up and run by CircleCI. In the job, we specify a working directory. This path will be used as the default working directory for the rest of the job unless otherwise specified. Directly beneath working directory, we'll specify primary container images for this job under Docker. In this section, we define the Circle environment. This environment is where our steps will be executed. On CircleCI, all the tests will be running inside containers. And in this container, we'll spin up our Docker app at Redis containers and run our tests. So basically, it's a container inside container. Sometimes we call it Docker in Docker. Now, we need to define the CI environment, which is the outside container. What we want is a Docker image that installs Docker and has Git. These requirements are satisfied by using Docker 7.05.0-c-git image, which is an official Docker image. When an image has the suffix -git, it means Git is pre-installed. By using this image, you ensure you're always using the latest Docker client. Now, we need to add several steps within the build job. The checkout step will check out the source code from GitHub to the working directory we have already defined. To build Docker images for deployment, we must use a special set of remote Docker key, which creates a separate environment for each build for security. This environment is remote, fully isolated, and has been configured to execute Docker commands. In general, if our build requires Docker or Docker Compose commands, we should add the setup remote Docker step into your .circleci config YAML file. Next, we install the Docker Compose in the CI environment through a Python-based package manager called pip. But pip is not pre-installed in the CI environment, so we'll need to install pip as well. Finally, we're ready to bring up our Docker containers and run our tests inside the containers. Now it is time to link CircleCI with your GitHub account. Here I am at the CircleCI website. Let's click Login. Then click Sign in with GitHub. If you have logged into a GitHub account in the same browser, you will be automatically logged into CircleCI. If not, try logging into a GitHub account first in the same browser before trying to log into CircleCI. Now we're inside CircleCI. What we're going to do is to add a new CircleCI project to run our tests. Click the Project tab, then click Add Project. Now, we go with the default options. We'll be running the test in Linux containers, and we'll go with CircleCI 2.0. Then we scroll down and click Start Building. So just give you a heads up that this build would fail, so don't be surprised to see a red failed build. I will explain why in a minute. I'm fast forwarding the video until the build is complete. Now, as you see, the build failed at logging into the Docker Hub step. This is because this build is running against the latest master branch, which includes publishing to Docker Hub. However, we won't inject the Docker Hub login credentials to CircleCI until the next lecture. Thus, this build failed as CircleCI can't find the correct Docker Hub login credentials. There's no action needed from you, just follow along. We'll fix it soon. So far, we have demoed how to manually trigger the build. As we mentioned before, the whole purpose of continuous integration is that a build will automatically be triggered when a commit is pushed to the central repository, so that if a defect is introduced to the code base, it can be identified and corrected as soon as possible. Let's prove that in a second. What we're going to do next is to check out a new branch of the v0.6 tag and make some dummy changes and push the changes to the central repo. We expect to see a new build automatically triggered, and this build should be green. This is because unlike master branch, v0.6 tag doesn't contain the publish to Docker Hub logic. Let's check out v0.6 tag first. Then we check out a new Git branch from our local repository. Just call it test-ci. And add a dummy file and commit it to Git. Then let's push the commit to GitHub. Oops, we need to set up the upstream branch for a newly created local branch. Just copy and run the git push command suggested by Git. After the push is complete, let's switch back to the CircleCI dashboard and refresh the page. See what happens? A new build is already running on CircleCI. This build should succeed. It proves our continuous integration workflow is set up correctly. CircleCI keeps monitoring our GitHub repository, and a build will be triggered automatically whenever new changes are pushed into the GitHub repository. Now, as expected, this build completes successfully. Let's quickly go through the build steps to see what happened during the build. First of all, CircleCI initialized the build environments. Next, CircleCI checked out the source code from the GitHub repository. Then, it created a separate environment for the build. Then, it installed Docker Compose. Finally, CircleCI started running our tests. That is the whole process of the build. That's it for the lecture, and I hope you have enjoyed it. In the previous lecture, we have seen how to link CircleCI with your GitHub account, so that if any new changes are pushed to GitHub, it'll trigger a build on CircleCI. In this lecture, we'll go even further to publish the newly built Docker image to Docker Hub if the test is green, so that we can pull the image from Docker Hub and deploy to staging and production afterwards. Let's see this in action. We'll start by creating a Docker Hub account. If you already have a Docker Hub account, feel free to skip this step. Now, I'm on the Docker Hub website. Just type a user ID, email address, and password. Docker Hub might ask you to verify your email address. After the verification, you should be logged into your Docker Hub account like this. In order to publish Docker images to Docker Hub from CircleCI, we need to have the Docker Hub account credentials saved somewhere. It's not a good idea to add the credentials to the Git history. Instead, we can add the credentials to environment variables to CircleCI. Let me show you in a second. Just logging into your CircleCI account and click the Build dashboard. Then click the Docker app repo. On the top right, click Project Settings, Environment Variables. Here, we create a Docker Hub user ID environment variable to save the Docker Hub user ID. A Docker Hub pwd environment variable to save the Docker Hub password. A Docker Hub email environment variable to save your Docker Hub email. Now we have saved those Docker Hub credentials in CircleCI. What we are going to do next is to add Docker image published instructions in the circle.yaml file. Here, let's go to your local Docker app repository, which you checked out in the last lecture. Make sure it's the forked repository under a GitHub account, not the original one. Otherwise, you would encounter permission issues when trying to push to the remote repository. Just do git stash and git checkout v 0.6 to check out the source code for this lecture. Then we check out a new branch called circle_ci_publish. Next, we open the config.yaml file under the .circleci directory. After the run key, we add a deploy key to configure publishing the newly built image to Docker Hub if all tests are green. We give this deploy section a name, Publish Application Docker Image. This name will be displayed for the build on CircleCI. Next, in the command section, we specify which Docker commands to run. The first thing we need to do is to log into Docker Hub using our Docker Hub credentials. To reference the environment variables, which we have saved in CircleCI, we need to put the $sign before each environment variable name. Next, let's tag our Docker image. Tagging images correctly is critical to maintain control and provenance for a container-based workflow. For any Docker image, we should be able to trace back to the exact Docker file and build context used to create it. For our Docker app application, we'll tag the newly built image with two tags. One is the git hash of the source code so that we can link an image with the exact Docker file and build context used to create it. The other tag is latest, which will always refer to the newest build that has passed our test. Now, let's issue the Docker tag command. We need to specify the Docker image name on the local box and Docker repository name we would like to tag on Docker Hub. Because we built the Docker image through Docker compose run command, the default local image name will be prefixed with the current directory name. In our case, it is Docker app. Let's verify that. Just run docker compose up-d to start all the containers. Then we run docker ps. See? The newly created Docker app image is named as Docker app_Docker app. The first Docker app is the name of our current directory. And the second one is the service name we defined in the Docker compose file. Now let's go back to edit the circle.yaml file. Just type the local image name. Then your Docker Hub account ID /Docker app. The tag we'll be used here is circle_sha1, which is a preset environment variable in Circle CI. And the value is set to the current git commit hash of the repository. Next, we tag the image with latest as well. Then, we'll push the image to Docker Hub. Now we have added the commands to push the image to Docker Hub. It is time for us to commit our changes and push to the remote GitHub repository. As before, we take the suggested git push command. The code has been pushed to GitHub. Now we switch back to the Circle CI account. See? A build has been triggered. After the build is complete, let's go back to Docker Hub account and refresh. See, we have a new Docker app repository. If we click the tag, we get two images. One is tagged with latest, and the other one is tagged with latest git hash. And those two images should be identical.